Good evening, everybody, and welcome to a Beneath the Surface lecture with Dr. Kerry Nickols, who you saw a sneak preview of her just a second ago. Um, we're gonna start here in just a second. We're letting everybody kind of sign in right now. So as we start to gather all of our attendees tonight, I just wanted to say how excited I am to have Dr. Nickols here to talk about climate change and its impact on the ocean. We have been working really closely just recently with Heal the Bay, and it's been amazing. I mean, we all have sort of the same goals and the same vision for the ocean ecosystem we have off of our coast. And being able to work with organizations like Heal the Bay, which has done so much amazing work for so long in our area, as well as the Bay Foundation and lots of others, our colleagues over at International Bird Rescue as well. Um, it really takes a team to get what we need to get done, and everybody pitching in their various areas. So really excited to hear about climate change, its impact on the ocean from the perspective of Dr. Nickols, who's has a wonderful background in all of this, but also to share this all with all of you, because you are also part of what helps to make this all happen. So without you guys, we would still be doing our best to do the work that we have, but we wouldn't be half as effective without the support of people just like you. So I want to say thank you, to everybody who's participating today and everybody who's watching on the recording, because it's really all of you that helps to make the difference. So we'll go ahead and get started. Today we have Dr. Kerry Nickols with us. She is the Director of Science and Policy with Heal the Bay, just recently brought onto the Heal the Bay team. And she's going to talk to us a little bit more about climate change, its impact on the ocean. We're going to learn about some of the things that we're seeing today, and things that we were just discussing, we've been talking about for the last, decades, 20, 30 years, about the impacts that we're going to start seeing from climate change. And we're seeing those things materialize now. Dr. Nickols is an interdisciplinary ocean scientist with experience working in the intersection of science and policy in California and internationally. Prior to joining Heal the Bay, Kerry was the program director of the Marine Ecosystems Repair Program at Ocean Visions. Before deciding to leave academia to focus on work in climate solutions, Kerry was an associate professor at California State University Northridge, where she studied coastal marine ecosystems and climate change, including the design and evaluation of marine protected areas and the potential for macroalgae to mitigate ocean acidification and hypoxia. She has served on state, federal, and international committees providing scientific guidance on ocean conservation issues. Kerry holds a PhD in ecology from the University of California, Davis, and a BA in earth and planetary science, as well as in integrative biology, from the University of California, Berkeley. Kerry is also, as you can see, a musician, dance music enthusiast, and I saw earlier we might get a cameo from her dog. Who's here. She's a pug mom as well. So Kerry, welcome to the panel today, or the panel of one. Welcome to the lecture.
Thank you. Thank you so much for having me, Dave. It's been really great getting to know the Marine Mammal Care Center and really looking forward to continuing to collaborate on all of these important issues facing the ocean.
Yeah.
Let me go ahead and
Yeah,
share.
go ahead and bring up your slides. And while you're doing that, I wanted to let everybody know that before we get started, I want to make sure everybody knows how they can donate to support work like we do at the Marine Mammal Care Center and lectures like this in the future. You should see a link in your chat function that can take you directly to make a donation. If you're joining us on a mobile phone or a mobile app, you probably won't be able to see that, or you might be able to, but if you can't, you can go directly to our website at marinemammalcare.org and make a donation there if you want to see lectures like this in the future and to support the critical work that we do. So without further ado, Kerry, take it away.
Thank you.
Sorry, don't take it away just yet. I forgot
Oh,
to do more things. Kerry's going to give us a talk today. We have two options for communicating with us. We have the chat function, of course, and um, Ashley, Quincy, and myself will be on there to help with any questions you have there. But if you have questions for our for Dr. Nickols, you can use the Q&A function of the webinar, and in that way we can see the questions that you have, and at the end of our lecture today, we'll be able to answer those. So make sure as you have questions, if you think about them, make sure you type them in there so you don't forget about them. Okay, I think now we've done it. So Kerry, go ahead, take it.
Excellent. Great. Thank you so much. Okay, first, I would like to recognize that I live and work in Los Angeles and that I am on unceded Indigenous land, and I want to pay my respect to elders past, present, and emerging as they continue their stewardship of these lands and waters. So today, just to give you an idea of what we're going to talk about today, I'm going to give you just a tiny brief taste, an introduction to who Heal the Bay is and who I am. But the bulk of the time is really going to spend on talking about climate change. So we're going to talk about some background information about climate change, and then spend a lot of time talking about some of the ocean impacts of climate change. And my goal here, I'm going to emphasize some of the physical and chemical processes that are driving climate change, with the hopes that everybody here can leave with a better understanding of why some of the things are happening that are happening. I'm going to also discuss some of the actions that we can take, and then of course there will be time for Q&A. Heal the Bay is an environmental nonprofit that was established in 1985 that's dedicated to making the coastal waters and watersheds in greater Los Angeles safe, healthy, and clean. We use science, education, community action, and advocacy to fulfill our mission, and I lead the science and policy wing of Heal the Bay. Our priority areas, and this is especially thinking about looking forward into this next year, are clean water, as it has been since the inception of the organization. We're also putting more and more attention into coastal resilience. And so thinking about ways to safeguard biodiversity, we do some work related to marine protected areas, and then getting deeper into addressing climate change impacts. And then we also do some work around single-use plastic reduction. And in particular, we have a bunch of work in advance of the Olympics that will be happening in Los Angeles. I am a lifelong Californian. I grew up in San Diego, and I have always loved the ocean, which I think likely goes back to my ancestors. And when I went to university at UC Berkeley, actually didn't think I would become a scientist, but I just really, really loved the ocean. And so I explored the ocean through different classes and eventually got scuba diving certified. And that is pretty much what ruined me and made me fall even deeper in love with the ocean. And I got certified, scuba dive, began observing, studying the underwater world, and ended up building a career in academia that was studying both the physics as well as the biology of the ocean and how they interact with each other. And over the course of my career, I've been really fortunate to study and learn from coral reef ecosystems, different places around the world, polar systems in Antarctica, but mostly I did work in kelp forests along the coast of California. And I'm really lucky to have been able to build relationships with these different places and organisms on and in the water. And also because I spent so much time underwater, it also meant that I was witnessing changes that were taking place because of climate change and other impacts, largely from humans. From seeing bleached corals in Moorea in French Polynesia to the loss of kelp forests, to urchin barrens from marine heat waves and other human drivers, I was deeply impacted by the things that I saw. And I did work hard to make my research available to policymakers, to the public, and to really do science for service. But ultimately, a few years ago, I decided to leave academia because I really wanted to focus more on solutions. And so I'm really happy to be now with Heal the Bay, leading their science and policy program. Now, before I go too deep into climate change, I want to kind of ground us in some amazing things about the ocean. The oceans contain 97% of all water on Earth and 99% of habitat. So places where organisms live, 99% of that's going on in the ocean. Depending on who you talk to or which website you read, between 50 to 70% of oxygen in the atmosphere, so oxygen that we're inhaling when we breathe, is produced by marine organisms. So you can think at least every other breath that you take in, you can thank the ocean for that. And the ocean is really important to humans. Over a third of the total human population lives within 62 miles of the coast. And in the United States, 39% of the US population lives in a county that's directly on the coast. Now, when we think about the ocean, I think a lot of folks are used to seeing this kind of view, although this picture I think I might have taken in the Southern Ocean, so maybe this isn't actually the ocean that you would think of. But you look out and you see this expanse, and sometimes it's really hard to see firsthand some of the impacts that are going on in the ocean unless you dive below the surface. And so, for a lot of us, the impacts of climate change and other impacts are just not really that apparent. So that's one thing to consider as we move forward. And then the other thing I want to emphasize is that the ocean is not separate from the rest of the planet, and the ocean is certainly not separate from the atmosphere. And so, what we're doing as we are burning fossil fuels and releasing greenhouse gases into the atmosphere, that is integral to what's happening in the ocean. The ocean and the atmosphere are exchanging gases all of the time. Temperature ends up equilibrating between the ocean and the atmosphere. The ocean drives what happens in the atmosphere. It drives our climate, it drives our weather patterns. So, it's really one system. And so when we talk about climate change and when we talk about the climate crisis, it's also about ocean change, and it's an ocean crisis as well. So a brief overview of climate change. Climate change is caused by, so this, you might see this word a lot in terms of, like, if you read about climate change, anthropogenic, that means human caused. So it's human caused production of greenhouse gases. Most of that, 95%, is a combination of carbon dioxide and methane. And what are greenhouse gases? They are gases that trap heat from the sun. And they occur naturally, and this is a natural process. And it's actually really good that we have greenhouse gases on our planet, because otherwise we wouldn't be able to live here. It would be too cold. So there's this natural process where these gases trap heat, and you can think of it as, like putting a blanket on. But what has happened with humans burning fossil fuels is that we're emitting more greenhouse gases, and they're trapping more heat and causing additional warming on our planet than there would be otherwise without those inputs. And if we look at measurements of carbon dioxide, which is here shown on the red axis in parts per million, that tracks right up with temperature when we look at measurements that have been collected. So there's a very, very strong relationship between the temperature and carbon dioxide. It's very well established. What we know about carbon dioxide concentrations and how they have varied, especially recently, comes from this really cool data set that's collected by Scripps Institute of Oceanography at University of California, San Diego. And this time series was started by Charles Keeling, who I think started it when he was actually at Caltech in Pasadena. And he was really interested in trying to understand natural fluctuations of carbon dioxide in the atmosphere that have to do from plants. So plants are taking up carbon dioxide and producing oxygen. In certain times of the year, there's more plant material than in others, like in the winter as things start to die back. So then there's more release of carbon dioxide during this period. So that's why this time series was started, was because he was really interested in natural fluctuations of carbon dioxide. And so he started taking some measurements in different places around the world and found that he needed to be somewhere that was a little far removed from big cities and from the continents because he was seeing a signal of pollution in some of the data. So in 1958, this time series was started on in Hawaii at the Mauna Loa Observatory. So you can go to this website, healingcurve.ucsd.edu, to see the latest information in terms of the carbon dioxide that's occurring in our atmosphere. So I have the latest reading up there, and this is from when I pulled it off the website just a couple days ago. This work is continued actually by his son, who maintains, who's also a professor at Scripps, and who has maintained this record after the death of Charles Keeling. So this figure here is just showing you what it looks like over the course of a year. So you can see that there's a rise in carbon dioxide concentrations and then it decreases. And this is, again, from atop a mountain in Hawaii. This is showing you the full record. So again, the record was started in 1958. So this is the full record from that observatory of carbon dioxide concentrations in the atmosphere. And you can see this yearly cycle that's happening, as we discussed, but then also this increase over time. There's another way where we can go further back in time to look at carbon dioxide concentrations, and that comes from coring through ice, because as ice is formed, it preserves the gases of the atmosphere at the time that the ice froze, which is like kind of mind-boggling. So scientists have taken cores of ice in Antarctica. This particular core, the Vostok core, goes down 2.2 miles. And then through some different techniques and looking at the different gas concentrations, they can reconstruct how much carbon dioxide was in the atmosphere in the past. So this next figure shows you the observational data from the observatory, and then it also shows you the ice core data, which this is looking back then at the last 300 years from the start of from before the start of the Industrial Revolution. So you can see this, steady increase over time, but has really shot up a lot during modern times. And then also with this ice core data, we can go back 800,000 years. And so you can see that there are natural fluctuations in the amount of carbon dioxide that's in the atmosphere. Ice ages have, these different cycles, natural cycles of the Earth, and the Earth in alignment with some other, with the sun. And we get these fluctuations that occur. But if you look over to the right, there's this really, really sharp increase, which also just drives home how fast this is happening and also how much more carbon dioxide we're seeing in the atmosphere than we had before, at least in the last 800,000 years. So we are seeing unprecedented levels of carbon dioxide in the atmosphere and an unprecedented rate of rapid change. So this is happening really quickly and likely on a time scale that is really, really challenging for organisms to adapt to and to change. So moving on into the consequences of climate change for the ocean, we're going to talk about warming. We're going to talk about changes in ice, which are really important drivers of some of both warming as well as when we talk about sea level rise. We're going to touch on then the more kind of chemical sides of climate change, ocean acidification and deoxygenation. And again, I just want to emphasize that I'm trying to kind of go over why some of these things are happening, and we'll talk somewhat about the impacts to biology. But I really just I hope that everybody's able to walk away understanding why some of these things are happening. And also, these things are all happening now. So that's an important thing. We're already seeing all of these aspects: warming, changes in ice, sea level rise, ocean acidification, deoxygenation. Deoxygenation means decreasing levels of oxygen. These are all happening now, and the impacts are going to increase. So this figure is showing you, so a lot of the stuff that I'm going to show you comes from the Intergovernmental Panel on Climate Change. That's the little acronym that you see at the bottom where I've put like the source of this figure. So the IPCC is a intergovernmental body of scientists that get together and they evaluate the science of climate change. The IPCC does not produce its own science. It synthesizes what is known about the science of climate change. And they update over every about 7-ish years, there's a new report that comes out. So the last one came out in, some of the reports came out in 2021, another part of it came out in 2022. And a lot of figures about climate change, what they'll show you is a parameter like temperature, for instance. Here we're seeing global surface temperature, but it's relative to a time in the past. So that we're looking at how much change there has been relative to that time. So this is looking at global surface temperature that's relative to the time period of 1850 to 1900. And the reason I picked this particular figure is because it shows you what's happening in the land and it shows you what's happening in the oceans. And all of these are going to be in Celsius, but I've also included what the Fahrenheit is. And I tried to also do that for feet meter stuff. So there's science units, and then there's how we measure things here. So one of the things to note here is that temperature is increasing faster over the land than it is increasing over the oceans. And that is largely due to the fact that that water is more dense. And so it takes more energy to change the temperature. And it's also the way that energy moves through the water. It takes more energy to heat the same amount of water than it does air. So the oceans have actually done us this incredible service by absorbing a lot of the heat energy that's been released from climate change. And it's actually over 90% of the heat energy from emissions of greenhouse gases has been absorbed by the oceans. So the ocean can take a lot before it starts showing a signal. But we're kind of getting to this point now where we're seeing increases in ocean temperature every year. There were some, record-breaking temperatures that have happened pretty recently. Another thing to consider about this fact is that once we stop emissions, the atmosphere will cool down more quickly than the ocean will because it's the same kind of thing. It's going to take, it still takes a lot of energy to change the temperature. So just keep that in mind. Some of the impacts of a warming ocean include increased stress to organisms, increased mortality. So some organisms, when they get overheated, will die. Increased metabolic activity or changes in feeding. So warmer temperatures in the water make a lot of organisms like they need more food because their metabolism has increased. There are changes in reproductive patterns. There are many examples of this across different organisms. For example, in sea turtles, the temperature of the sand determines the sex of the eggs, and so the sex ratios are being skewed as we're having more warming occur. We're also seeing brain shifts. So some organisms they aren't performing well as warming is occurring. And so they're actually showing up in places that are more poleward. So in our hemisphere, that means they're moving northward because they're having a hard time coping with the warmer temperatures. There's also changes in productivity and timing. So what this means is that as there's changes in reproductive patterns, there's changes in the phytoplankton, the tiny microscopic plants that are in the ocean. They are having changes when they are blooming and being productive, and then that can lead to consequences up the food chain. So if there is a particular fish that responds to a particular type of phytoplankton, and then that phytoplankton is blooming at a different time, then that fish isn't getting fed at the right time. And then if that fish is food for seabirds, for example, or marine mammals, then there are also problems. And again, these are all things that we're currently observing and will continue to see more of as climate change increases. And then another one is altered communities. So we're seeing the kelp forest urchin barren example is a classic example of this, where as kelp forests die back and urchins get a foothold into the communities, then it makes it harder for kelp to reestablish. And so there's been transitions from kelp forests to urchin barrens. Sort of the classic one that we probably think of when we think of temperature stress and warming and impacts on the ocean and marine ecosystems is coral reefs. Um, when coral reefs get stressed by increased temperature, they expel their algae that live inside of their tissues that give them extra food. It's also what gives them their color. So that's in that picture on the left. That's a healthy coral reef. So when they get stressed, then they eject their algae from their tissue, and then that doesn't necessarily mean that they die. If the temperature goes down and then the algae recolonize their tissues, then they're able to come back. But in this particular example, this is showing that same reef that was not able to recover and eventually it dies. And then it gets colonated by algae that are not, a totally different kind of algae. This is like a macroalgae that then grows on top of it and ends up like suffocating and smothering the reef. And one of the things that I want to mention too about temperature and warming and thinking about ocean impacts is that some organisms, so like in the tropics, temperatures, especially in the ocean, in the water, have been very stable. They don't change very much. And so organisms have been adapted to those temperatures. And so then when they see a temperature that's really far outside of the range that they're used to, it becomes really hard for them to cope with it. And it's the same thing actually in the polar region. So in Antarctica, it's very, very consistently cold. And so organisms have a hard time when it gets too warm and it's outside of what they're able to deal with. And then here's an example of warming impacts from Northern California. So back in around 2013 to 2016, there was this really big marine heat wave that occurred along the coast of California and up into Oregon, Washington, and Canada. And this is a different kind of kelp than we have down here in Southern California. This is the bull kelp. And because of this marine heat wave, about 95% of the kelp forest died and it has not recovered. And so some of these areas have transitioned into urchin barrens, and there's a lot of efforts by scientists and by nonprofit organizations to try to do some restoration of kelp in these areas. Okay, so warming is also causing changes in ice, which are a big deal. And really quickly, it's hard for me to find an appropriate figure that showed you some of these different types of ice because ice gets a little confusing. So over Antarctica and Greenland, there are these massive pieces of ice called ice sheets that can be 2 to 3 kilometers tall. And I'm sorry that I don't know the mile conversion right off the top of my head for that, but they are multiple miles tall. Those ice sheets then extend over the ocean if they're in areas like near the coast, and that area is called an ice shelf. Pieces of ice shelves break off, and those are icebergs, which you're probably familiar with icebergs. That is different and kind of on a different scale than sea ice. And sea ice is this really cool ice that forms every year. It expands and contracts with just natural temperatures, so in summer and winter. And it forms on the surface of the sea. And it's between about 3 and 10 feet on average thick. Um, and then there's also glaciers, which are in mountainous areas that sometimes can go into the ocean. And these are all of these types of ice that you see, they are all decreasing due to climate change. And here's just a picture showing you this is an ice shelf that's 1,000 to 2,000 feet thick, and then contrasting that with sea ice, which again is about 3 to 10 feet thick. Also, when we talk about ice, we have to talk briefly about the difference between Antarctica and the Arctic. So Antarctica is a continent that's surrounded completely by the ocean, which is why it has been so cold for a long time. Because it essentially has this like wall of cold water that's around it, and it's pretty isolated from the other continents and from the other ocean basins. The Arctic is the opposite. It is an ocean that's surrounded by continents, but it can look a little confusing because you're seeing that white blob in the middle. The white blob in the middle is sea ice that's covering the ocean in the Arctic. And then this area, I don't know if you can see my pointer, but the area that's kind of like bottom left that's white is Greenland, which is land that is covered in an ice sheet. So first, I'm going to talk about a little bit about Arctic sea ice and how much we're losing and why this is a big deal. So the figure on the top is showing in the yellow line that you can see is the average extent of sea ice that was occurring between 1981 and 2010. And then the white that you see in that map is showing you how much sea ice there was in 2023. And this is during I think that snapshot is from the summertime. And then the plot below is showing you time on the x-axis, and then the y-axis is, you can just think about it like amount of sea ice. And so it's each squiggly line is a particular year. The red one shows you what it looked like in 2023. And then the kind of darker green line shows you the average from 1991 to 2020. So Arctic sea ice has been doing, again, these features of our planet really provide us with incredible services. And so this shield, you can think of it as like a shield of sea ice that forms over the Arctic Ocean, has been really, really helpful in keeping our planet at a really comfortable level, keeping the temperature of the planet at a comfortable level, because bright white surfaces, they are reflecting heat energy back into space. So this is particularly in the summertime. So in the polar regions, it's pretty much dark all the time or sunny all the time. And so when it's sunny all the time in the summertime, it is really, really important that this bright white surface has been reflecting heat energy back into space. So sea ice loss then decreases that reflectivity. So as we lose the bright white surface in the Arctic and we have more and more ocean surface exposed, then that darker surface is absorbing more heat. And then that means even more warming, even more melting of sea ice, and so on and so forth. It's a vicious cycle. Arctic summer sea ice has declined 50% over the last 40 years, and sea ice showing up during the summertime is expected to not happen by the middle of this century under all emissions trajectories, if not earlier. So this is one of the first major physical consequences that are going to happen in our lifetimes because of climate change. The good thing about the sea ice, though, is if we did get temperatures back down, it would come back. The loss of sea ice is leading to loss of habitat for lots of organisms. It's impacting food for organisms as well as for people. There are a lot of negative impacts on indigenous people, both because they use sea ice as a way, as sort of like a highway for transportation, for hunting, and for accessing food, as well as because in coastal areas, sea ice can block erosion. There are security implications when we think about geopolitics in the Arctic for losing sea ice. And also there will be increased resource extraction once the Arctic becomes ice-free. So this is kind of an important one. Ice sheets cover Greenland and Antarctica, as I mentioned earlier. These maps, the colors, so the darker reds and into orange, that's areas that are losing ice mass. And then the white areas are no change, and then the blue is where areas that are increasing in ice, but there aren't that many of those. So Greenland is losing ice at a faster rate than Antarctica, and Greenland is currently is a larger contributor to sea level rise than Antarctica, but that will shift and change over time. And the reason that the ice sheet loss is really important is because of sea level rise. So the loss of sea ice does not contribute to sea level rise because that is turning seawater into ice. But the deal with the ice sheets is that that is ice that has been locked up on land, and then it's melting and going into the oceans. So sea level rise is increasing. This is a figure showing you a time series, and all these different colors are different data sets. So lots of folks have been measuring sea level rise. We are already at a global average of 0.78 feet of sea level rise, which maybe doesn't sound like that much, but if you live on a low-lying place, there are many places that are below sea level where people live. Um, then they're already experiencing large amounts of flooding. And this will continue to increase over time. What causes sea level rise? So I mentioned that it's melting ice that was locked up on land. So the melting of the ice sheets is the main contributor on the ice side. But there's another issue, and that is called thermal expansion. And this is that the fact that warm water takes up more space than cold water. And this has actually contributed to 30 to 55% of sea level rise. So at least, about half, a third to a half of sea level rise is because of warming. So it's a consequence of warm water that takes up more space. Um, This is a figure. So Climate Central is a really cool website. If you ever want to nerd out on climate change graphics and infographics, that is a really great place to go. But they did this whole series where they have different cities around the world, and then they've shown what present day sea level rise looks like, and then they also show future scenarios on top of that. And one of the tricky things about sea level rise is that there's a delay from when greenhouse gases are emitted into the atmosphere to when it manifests in sea level rise. So that's all to say that we're kind of already committed to a certain amount of sea level rise based on the emissions that we've already had, but we're not seeing those effects yet, but we will in the future. So this is showing you Santa Monica Pier. This is showing you, so the Heel of the Bay has an aquarium that's underneath the pier. And this is present day sea level. And then this is showing you unavoidable future sea level rise that's due to past carbon emissions. So this is going to happen eventually. This is kind of far out in the future. I believe this is thinking of like 2100 or beyond. So this is not happening tomorrow, but it is going to eventually happen. And for those of us, I personally don't live this close to the ocean. I live further inland. And so maybe it's easy for some people to think like, oh, that's okay. That's not really going to impact me that much. But there are many, many people, as I mentioned earlier, throughout the world that live below sea level. There are islands in the Pacific that have already purchased real estate from other countries they are planning to move their entire country to another country because their country will be uninhabitable. So this this is happening now, and it will continue to happen into the future, and it's going to lead to things, mass migration of people, in addition to obviously like you're completely changing habitats for marine organisms. So now moving on to some of the more chemical sides of climate change. So ocean acidification is another consequence for the ocean. And ocean acidification happens because the carbon dioxide, the chemicals in the atmosphere, they go into the ocean. And the oceans, again, doing incredible things for us. They've actually absorbed about 30% of the emitted carbon dioxide. but it's causing ocean acidification. So I used to say in my classes when I was teaching, I would like ask anybody if they had a soda stream. And then as the years went by, the students would just like look at me with blank faces, like, I don't know what you're talking about. But that's, that contraption. Actually have some water from a soda stream right here, where you are pumping carbon dioxide to carbonate, the water. Um, that's a lot of carbon dioxide. That's more than what's happening in the ocean currently. But as we're adding carbon dioxide, it's making the ocean more acidic, which means that the pH of the water is decreasing. This is really bad news for all of the organisms that that calcify. So corals, shelled organisms, it makes it harder and harder for them to make their hard parts. There's also other consequences for organisms that don't calcify, and we're kind of just starting to understand what some of those impacts might be. But pH is just a really important parameter for lots of organisms and how they, live and operate in their daily lives. Here's an example of an organism that's already being impacted by ocean acidification, which you've probably not heard of, but maybe because I think that there are some ocean aficionados in the audience that probably know about these, but pteropods, they are found off the coast of California, but they're also really, really common in the Southern Ocean, so around Antarctica. And they are these beautiful winged mollusks. And so their common name is sea butterfly. And so they have their like foot comes out and they fly, well, they glide through the water. And what you can see on the left is that's what their healthy shell looks like. And then on the right, you can see the damaged shell that has abrasions and dissolving ridges. And this is already happening where scientists will be in that region. They will take a water sample, they'll take a plankton sample, and they are already seeing pteropods with damaged shells from the lower pH waters. Another organism that's been sort of the poster child of ocean acidification are oysters. And this is maybe the first organism where it became apparent on the west coast of the US that ocean acidification is going to be a problem. There's several oyster farms along the coast of the west coast of the US where they're getting larvae sometimes from the ocean, or they're rearing these like little babies that they get from the local oysters that they have, but then they're being influenced by the ocean waters. And so there were multiple hatcheries that noticed that their larvae were having problems with their shells and that the shells were dissolving in different ways and were being impacted by ocean acidification. So there are some hatcheries that have already taken measures. They actually grow their larvae, they grow the babies in Hawaii, and then they bring them back and grow them out when they're bigger. This is again, a problem that we're already seeing that this industry is trying to adapt to. But you can think of like the local oysters don't have that luxury to, that are living in the wild to send their babies to Hawaii. And then the final consequence for the ocean that I want to talk about is deoxygenation, so declining oxygen concentrations in the ocean. This figure is showing you a map of the world's ocean, and the red areas are where we have seen a decrease in oxygen. Then there are some special areas where you see blue where they have seen an increase in oxygen. The top panel is showing you like the upper, about a mile or so of the ocean, and then the deeper ocean floor is shown in the bottom panel. And why this is happening, basically, the oxygen concentrations are declining because the oxygen in the water is being used up faster than it's being replenished. And another factor is that warm water holds less dissolved gases, and also that warm water is decreasing the amount of ocean mixing that we have. And then coupled with that, warming increases oxygen consumption. So I talked earlier about some of the warming impacts on organisms, that it increases their metabolism, it increases their feeding. So that also is leading to more oxygen consumption. And then there are other inputs from humans, like inputs of nutrients, that also increase oxygen consumption and are leading to this issue with decreased oxygen concentrations in the ocean. When we have times where there's really low oxygen, then it can lead to pretty horrific things like mass die-offs of marine organisms and create dead zones. So this figure or this picture is from an event that happened off the coast of Oregon, where there was really, really low oxygen in the waters that got close to shore, and there was a mass die-off of marine invertebrates. Okay, so we talked about these different consequences for the ocean in terms of climate change, but they're not operating in isolation. So these consequences interact with each other, and then they also interact with other stressors from humans. So thinking about overfishing, nutrient pollution, these are additional stresses that can magnify the effects of climate change in the ocean and on the organisms that live in the ocean. This figure is from the IPCC, and it's kind of summarizing in a way, thinking about all of those different impacts from climate change and what they might mean for different ecosystems. And so really what I want to draw your attention to is just that if you're purple, your risk from climate change is really high. If you're yellow, it's maybe not going to be as bad. And so warm water corals are really not doing well and are going to continue to not do well with the added impacts and risks from climate change that we will be seeing in the future. This is showing you the gray bar is showing you present day, and then as you go up along the scale, it's increasing in temperature. Another one is kelp forests. So kelp forests, they're kind of doing okay right now, but as we get warmer, they're also going to be having a hard time and face more and more risks from climate change. So limiting climate change will require substantial and sustained reductions in greenhouse gas emissions. And like, it's not going to be easy, but this is what has to happen. The good news is that we know what we need to do, and so we just need to do it. So what needs to happen? We have to stop burning fossil fuels and releasing greenhouse gases. Probably easier said than done. In the US, what does that look like? 28% of emissions come from transportation, electric power 25%, industry 23%, residential and commercial make up a smaller percentage at 13%, and then there's also emissions from agriculture. But an important thing to know about the United States is that we have both the highest cumulative historical emissions. So over time, the United States has released the most emissions of greenhouse gases out of any other country. And we are also among the highest in terms of per person emissions of any country. So this is just showing you, like on the x-axis is the cumulative emissions and then different countries. And really the point here is that the United States. Oh, what does emissions mean? So emissions means the amount of carbon dioxide that has been released through burning of fossil fuels. Or in this case, there's also burning of fossil fuels. Cement also releases fossil fuels, and then land use changes is another component. But United States has done the most. Also, important to know that, and there's a lot going on in here, but really the thing to focus on is that the richest 1% of the people on the planet have led to the largest amount of emissions per person. And you can see over here, like on the right, that's the global average. So how much emissions that's responsible per person. So I think one of the problems with climate change and to think about what to do with it is that there are some really awful impacts that the world's most vulnerable, the poorest people living on this planet are going to be really, really impacted, and they were not responsible for those emissions. And I don't want to say this to like guilt us all for living in the United States, but there are also things that we can do. There are some, I'm calling them pretty easy actions for you. And it might not seem that some of these are easy, but it's really going to require us all trying and to get enough people so that we can scale up some of the solutions. So if there is any way to electrify your home or to use renewables, that is great. You might live in a place where, like for me, solar actually, I have a pretty small house and I don't actually use that much electricity. And so solar would be kind of prohibitively expensive for me to get on my house. But there is a program through LADWP that I elect into where I pay a tiny, tiny bit more on my electric bill, but it ensures that all of my electricity is coming from renewable energy that LAWP DWP is responsible for. So there's different programs like that. Also, reducing food waste and compost. We didn't get into the details of carbon dioxide versus methane, but methane is a really, really potent greenhouse gas. And if we do action on methane, then it will make kind of an outsized impact. And food waste, like if you don't, if you have fruits and vegetables that you didn't eat and then it just goes in the landfill, that's actually as they break down, it's releasing methane, it's releasing greenhouse gases into the atmosphere and contributing to climate change. But a lot of cities have really great composting programs, and so that is actually something that's pretty important that you could do. We also need to start thinking about adaptation measures. There are things like stormwater capture, so trying to be really wise in our water usage, and because that's going to become an ever increasing issue. Reducing the amount of nutrients that go into the ocean, because that again causes a sort of additional stress on organisms, and it also has an interplay between the other aspects of climate change. It can increase things like harmful algal blooms. There are some really, really cool projects locally to start thinking about having favoring living shorelines over hard armoring that can help with sea level rise. Um, and also starting to think about managed retreat. So, where do we maybe need to move development and buildings away from the coastline because there's an inevitable amount of sea level rise that's going to occur. Um, this I just wanted to, and actually I'm cognizant of the time because I want to make sure that we have time for questions. So um, this is a figure from the IPCC that's just pointing out some ways in the ocean that we could adapt. And I just want to point out that there are some really cool things that are happening right here in California, and in fact, right here in Los Angeles, about trying to restore different areas. We have an incredible network of marine protected areas in California, and these are also avenues for people to kind of get involved. You can support scientists and nonprofit organizations that are doing some of this work. Eating sustainable seafood can make a pretty big, important difference. And the California Marine Protected Area Network has a number of different ways to get involved, and I'm happy to point people towards resources if they're interested in that. Um, there's also a recognition that having some of these restored habitats, so having things like healthy seagrass and healthy kelp forests, can also help us deal with climate change impacts. So seagrass and kelp, they're uptaking carbon dioxide and releasing oxygen. So there's all of these like win-wins between having healthy marine habitats and a healthy ocean and trying to mitigate some of the impacts from climate change. So stop burning fossil fuels and releasing greenhouse gases, start thinking about adaptation. We also are going to have to think about removing carbon dioxide from the atmosphere and from the ocean. This is something that is kind of in its infancy, but something that you will hear more and more about as the years go on, because if we want to bring temperatures down, we're going to have to remove carbon. And then there's also a lot of research into other options to try to lessen the impacts of climate change. And as the impacts of climate change increase, again, this is an area that you're going to hear more and more about. Things like favoring lighter colored surfaces because they reflect sunlight as opposed to like really, dark asphalt that's absorbing a lot of heat. But also some other types of things that might actually change the amount of sunlight that's entering Earth's atmosphere. So I don't want to scare anybody, but I just want you to be aware that these things are going to be more and more at the forefront, and you're going to hear about them more as the impacts to climate change increase. And so I think it's just important that everybody is aware. If you want to know more about really in-depth things that would make a difference for climate change, there's this really cool website, Project Drawdown, drawdown.org, and they have really, really detailed information about ways that we can try to reduce the amount of greenhouse gases in the atmosphere. And then I personally think that the number one thing that you can do to address climate change as well as other issues facing the oceans is to talk about it, because for a lot of people, this is kind of an out of sight, out of mind thing. It's going to more and more not be that way. And we saw that with the horrific wildfires that devastated Los Angeles last year, that um, it's just going to become more and more prominent, and we need to be talking about it. We need to be challenging each other to do something about it, and also challenging our elected officials, the businesses, industries, who really have a lot of power in the situation. So I know that was a lot. Thank you for bearing with me, and I hope that you learned something. I'm happy to stick around as long as it takes, and as long as everybody else, as Dave is willing to stay to answer your questions.
As long as it takes, for sure. Thank you, Dr. Nickols. Big round of applause. You can't hear it because they're all on Zoom, but they're
Great,
applauding too.
great.
Thank you so much. And I want to highlight, you mentioned LADWP, and it's an important partner. It's a partner that we have at the Marine Mammal Care Center. And what I think is really great about that is it's something that we can all join in on. LADWP has a plan to go carbon neutral by 2035, which is not that far away. And if we could do that in such a large city like Los Angeles, then you could do it anywhere. And it also goes to that talk about it point that you were making in the end, that what we really need to do is do the biggest thing that we can possibly do, right? And by the way, guys, I'm sort of stretching here, so if you have any questions, you can put them into the chat or put them into the Q&A as well. And Brad, we'll get to your question. But when you talk about it, about it in the biggest way you possibly can, right? So if talking about it means you can share with your friends and family, great, you should do that. Use Thanksgiving, it's coming up. Talk about climate change. If you can do it bigger, if you can do it within your community, maybe at your church, maybe as part of a community group at the YMCA, do it there. If you can talk to your elected officials, that's an even bigger way to talk about it. And I always challenge people to go as big as you possibly can when having those conversations. Okay, we have some questions here. Let's see. Can you talk about conservation policies or initiatives that you and your team are working on right now? Do you have anything in the hopper at Gila Bay?
Yeah, that's a great question. So a lot of what we do and have done historically has been around like water issues and stormwater issues, and thinking about water that's entering the ocean, and how we can make that water better for the ocean, like like thinking about decreasing the amount of nutrients. So when Heal the Bay was started, it was started because there was a lot of nutrient pollution in Santa Monica Bay, and it was depleting the oxygen. So what I talked about earlier, and leading to these dead zones and like really obvious negative health impacts on marine organisms. And so by changing the way that water was being treated, the Santa Monica Bay like bounced back. And so we have seen what can happen when communities and people get together and try to like push for action. We can see, ecosystems rebound. More specifically on the climate front, after the wildfires that happened, and particularly the Palisades fire, Heal the Bay was actually like the first on the scene taking water quality measurements to see about the impacts from wildfires as they affect the ocean. We're continuing to collect samples in response to the rain events that were happening. So actually gearing up to get out after this next rain event that's predicted for the weekend. And then in kind of like the bigger climate sense, I'm trying right now. So I just joined Heal the Bay recently, and I'm trying to understand what different organizations and entities are doing in the area around climate to figure out where is a really good place for Heal the Bay to, add value to what's already happening, thinking about joining coalitions, et cetera. So, for those of you on the webinar who maybe are working in the climate space, would love to get your feedback on where you see action being needed by a local ocean organization.
Dr. Nickols, we had a question, and maybe this is beyond either of us, but given that we're going to be losing so much of the sea ice in the Arctic, are there any plans that you know of for organizations or people to try to preserve some of the biodiversity that might be lost with that lost habitat?
Yeah, that's a great question. And in my um, the last position that I had before joining Heal the Bay, I worked on Arctic sea ice, which is why I like also talking about it because I've learned a lot about it. But there are a lot of efforts to put in to protect more of the Arctic. There's a group, so there's actually a really great fisheries agreement that already exists, the Central Arctic Ocean Fisheries Agreement, which has put a kind of a moratorium on fishing except for research purposes. So that's like one of the good things is that as it stands now, there's actually not a lot of fishing happening in the Arctic Ocean. That might change over time. There are several, like the World Wildlife Fund and some other organizations are trying to put more marine protected areas in the Arctic area. There's also people that are doing research into are there ways that we could increase the amount of sea ice? So these would be considered climate intervention. So there's a couple groups doing research on pumping water from the ocean on top of the sea ice surface to try to thicken the sea ice so that it lasts longer. So there's definitely a lot of people thinking about this and trying to do things to understand it.
Yeah, definitely a really, really tough thing. How do you
Yes.
preserve something that's locked to living on sea ice when the sea ice doesn't exist anymore?
Yes.
Um, so we had a question. You mentioned marine ecosystem adaptation approaches. Can you explain a little bit more about some of the ecosystem adaptation approaches? I also want to mention Altasea is a local partner that we work with. And at Altasea, they're looking at growing seaweed. You'd mentioned, we might be able to capture some carbon, and seaweed might be a way of doing that.
Yep. Yeah, so there are people looking at the capacity of kelp and other algae to take up carbon dioxide and to maybe grow them in strategic areas. Also trying to understand, there's a lot of research trying to look at what does kind of the current landscape of ocean conditions look like now? Where are areas that maybe already for a long time have seen higher temperatures versus lower temperatures? And are organisms that live there maybe better adapted to the changes that we're seeing in the climate? So maybe we should protect those particular areas so that the species that might do better under increased warming, will have less stressors to worry about from like fishing or maybe nutrient pollution so that they can really thrive there and maybe they can help then start to populate some of the other areas when they start having trouble. So those are just a few different examples of those types of projects that are going on.
Cool, thank you. And let's see, James Wang was the one who asked that question, and he wanted to specifically know who is evaluating the different marine adaptation approaches, such as marine conservation areas, MPAs, assisting species, like criteria and things like that. Um,
Yeah, so with the marine protected areas, so the Marine Protected Area Network in California, that is managed by the California Department of Fish and Wildlife. Um, we have the second largest network of marine protected areas in the world, and it's this really incredible thing that we even have these marine protected areas. So I just want to lead with that. So they have been around for over 10 years now, the full network, and it just went through an evaluation process. When that Marine Protected Area Network was designed, they knew about climate change, but I wouldn't say that climate change played that much into the design of the network. So I think there's an opportunity as we look forward to think about, are there adjustments we would want to make to the network, in particularly thinking about climate change. So, if there are areas where maybe there's this like, really interesting oceanographic situation where it's not going to get as warm as some other areas and organisms are thriving there, then maybe we should really think about protecting that particular area. So this is something that there's scientists at different universities across California are thinking about, as well as, again, the California Department of Fish and Wildlife.
Um, I want
Yeah.
to I want to share John Warner, our CEO. He is a verdant advocate of composting as a mitigation means to climate change. Everybody who is part of LADWP has received their little compost bucket for use in home. And if you didn't know, you can place your compost in the green bin. So the green bin that you have isn't just for yard scraps. You can also put your compost in there if you don't have a compost bin at your home. Um, all of those things are possible at home. Vermiposting, lots of things you can do, even in smaller homes, apartments, things like that. That can help. Every little bit is going to help with that, and it makes the best planting material, especially vermiposted materials. Uh, Denise is asking, do you know anything about the artificial ice structures that some countries are thinking about?
I I am not aware of these for this purpose. Um, but that's a really interesting idea. So it's about trying to give seals and penguins places to give birth on and raise their young as the ice decreases. But I think this is a really good example of human ingenuity and innovation and the possibility for humans to try to come up with ways to deal with some of the changes that we're going to see and to try to give the organisms that are being impacted by climate change kind of a better chance to go forward. So I think, we can't really look at humans and the planet and nature as separate. We are integrated and we need each other, and we were a part of creating this situation, and we are going to be the solution. We're going to be a part of the solution. And so, you know, now's the time to get your creative thinking caps on.
And everybody that's part of the discussion tonight, participating in this, you are participating. You are part of the solution. I just want to share ideas like these are great, um, but we have to scale them. So when
Yes.
you think about the scale of the loss of Arctic ice, we're talking about the size of very large countries, being lost. So we would need to recreate the amount of space that many very large countries. So when we talk about growing kelp to mitigate against carbon, it's like growing kelp in an area the size of your favorite small state to even start making an impact.
Yeah.
So we need to go big. But what's great is we have all of the solutions. we don't need to innovate. I mean, innovation is going to help, right? We're going to have new inventions, new ideas. All of those things are going to help us to get to our goal, but we don't need anything new. If we stopped today, applied the things that we know today, we could turn this all around. And we're starting to do that. LA, DWP, taking us to carbon neutral by 2035. We could get more aggressive. We could do it sooner. But it's going to take all of us to participate in making that happen. Um, so there's a question for Mickey about any progress made in changing the blacktop streets into lighter colors. I think that's always been floated out there, but do you know of any municipalities or anything that's actually putting that into action?
Um, I don't locally, but I also haven't really looked into it, if I'm being honest. So,
This is one of those things that using our voice, talking about it, and sharing at a local level, what color our streets are, could very well be your local city ordinance, right? That you could talk at a city council meeting. You don't have to go as far as state or federal to change some of these things. You can do it at a very local level.
yes, definitely. And it looks like James Wing in the chat said that Arizona, among other states, is looking into it. So yes, definitely no. And there have been a lot of efforts to also, like some playgrounds have had, dark surfaces, equipment that gets really hot, and there has been, I know, a lot of local efforts to try to change that.
Yeah, planting trees as well. Getting more shaded surfaces. Trees do a lot, but shade is one of the things that they can help with. And we can think about that as in the adaptation sense. If we add more shade to our cities, we're not necessarily changing the overall temperature of things, but creating areas that might be cooler than they would otherwise be,
Yeah.
to mitigate against some of those impacts. Dr. Nickols, thank you so much for joining us today. This was awesome. I really appreciate you taking the time. I deeply appreciate the connections that we have with Heal the Bay, in helping us to get to that same shared goal, which is, an ocean that is not as challenged as it is right now. And everybody on the call today and everybody in our organizations, that's what we're working for. So thank you, and thank you all for participating. We'll have more Beneath the Surface lectures coming very soon. So keep an eye out for advertisements. We're going to talk more about this. If you come to the Marine Mammal Care Center, we would love to have you come down. We have a sign now that's all about climate change, its impact on the ocean, its impact on marine mammals, and solutions. So if you want to learn more about it, you can go to our website to learn more about it. Especially some of those initiatives through LADWP. And you can come talk to us down here at the center as well. We would love to engage in this conversation more. So thank you all for joining us, and I wish you all a great evening.
Thank you all so much.